Hello there, and welcome to Science Documentary for Sleep. Tonight, I'd like to spend some unhurried time with galaxies, not as distant spectacles or dramatic backdrops, but as real structures, governed by simple physical laws, unfolding slowly across deep time. This is a documentary in the truest sense fact-centered, observational, and patient. You can listen closely or loosely. Nothing here needs to be memorized. Understanding, if it arrives, can do so gradually and at its own pace. I'll be here as a human host, guiding the thread of ideas, not testing your attention or demanding it. The science will remain precise, but never hurried. And if at any point your focus drifts, that's entirely acceptable. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. You're welcome to share where you're listening from, and the local time around you. Let's begin. As we move gently forward from the opening, nothing really changes in tone or pace. The topic remains galaxies, and the intention remains observational rather than dramatic. I'm simply continuing the same quiet thread, allowing the idea of galaxies to settle without pressure. You might picture a dark field, not empty, just vast. There is no motion yet, no spinning arms or glowing centers, just space that feels open and unmeasured. A galaxy is defined, in the simplest scientific terms, as a gravitationally bound system of stars, gas, dust, and dark matter. Gravity is the single organizing force here. It holds everything together across distances so large they are usually measured in thousands of light years. A light year is a unit of distance, not time, describing how far light travels in 1 year through empty space. Using that scale keeps the numbers manageable for astronomers, even though they remain immense. The significance is quiet but fundamental. Galaxies are the largest organized structures made primarily of stars. You don't need to picture the full scale precisely. Just noticing that such structures exist at all is enough for now. And as this idea settles, the mind doesn't need to hold it tightly. It can remain loosely present as we continue. That sense of vastness continues naturally, without needing to be reinforced. Nothing new has interrupted the flow. We're still standing at the same conceptual distance, simply looking more carefully. Imagine a single galaxy suspended in darkness, its edges fading gradually rather than ending sharply. There's no clear boundary, only a thinning of stars as distance increases. Most large galaxies contain hundreds of billions of stars. The exact number varies, but even smaller galaxies may host millions. These stars are not packed closely together. On average, they are separated by several light years, leaving enormous regions of empty space between them. This spacing is important. Despite the large number of stars, galaxies are mostly empty volume. Collisions between stars are extremely rare, even in dense regions near galactic centers. That fact matters because it explains why galaxies can persist for billions of years without destroying themselves through internal chaos. As an observer, you can simply note that density and emptiness coexist here without conflict. The idea doesn't demand resolution. It can remain open, spacious, and unfinished as we move on. The image of a galaxy suspended in space remains steady as we continue. There's no need to shift focus abruptly. We're still examining the same object, just from another quiet angle. You might now imagine time passing instead of distance. Stars continue shining, slowly changing, while the galaxy itself remains largely intact. Galaxies are long-lived structures, Many have existed for more than 10 billion years. Their overall shapes can persist even as individual stars are born, evolve, and eventually fade. This persistence comes from gravitational balance. The combined mass of stars, gas, and dark matter creates a stable system where large-scale changes happen very slowly. To clarify, galaxies are not static. They rotate, interact, and sometimes merge. But these processes unfold over hundreds of millions or billions of years, far beyond human timescales. The quiet significance is that galaxies provide continuity across cosmic time. You're free to notice how different this timescale feels from everyday experience. There's no need to reconcile that difference. It can simply exist as background as the narrative continues. That long sense of time carries forward without interruption. We haven't left the galaxy behind. We're still observing it as a whole, allowing details to emerge gradually. Picture the galaxy now with subtle motion. Stars trace slow paths around a central region, like a calm, nearly imperceptible drift. Most galaxies rotate. This rotation is not rigid, like a solid object, but differential. Stars closer to the center orbit faster than those farther out, responding to the distribution of mass within the galaxy. This behavior provided early evidence for dark matter. Observed rotation speeds could not be explained by visible matter alone, implying the presence of additional unseen mass. Dark matter does not emit or absorb light, but its gravitational influence shapes galactic motion. The importance here is structural rather than mysterious. Without dark matter, galaxies as we observe them would not hold together. You don't need to picture dark matter directly. Just acknowledging its gravitational role is enough. The idea can rest here, unfinished, as we move gently onward. Nothing new needs to be introduced yet. The galaxy remains our reference point, steady and familiar in its vastness. You might imagine the galaxy's light traveling outward, spreading into surrounding space, thinning as a distance increases. Galaxies are visible because of the light emitted by their stars and glowing gas. This light can travel for billions of years before reaching a telescope or an eye. When astronomers observe distant galaxies, they are seeing them as they existed long ago. A galaxy 1 billion light-years away appears as it was 1 billion years in the past. This is not a special effect or distortion. It's a direct consequence of light having a finite speed. The significance is gentle but profound. Observing galaxies is also observing cosmic history. As a listener, you can simply notice that looking outward in space also means looking backward in time. That idea doesn't need closure. It can remain open, quietly expanding as we continue. The sense of looking outward and backward continues smoothly. Nothing has shifted suddenly. The galaxy is still there, unchanged in its presence. Imagine many galaxies now, scattered across space, each one a separate system with its own history. Galaxies are not evenly distributed. They tend to form groups, clusters, and long filaments separated by vast voids. This large-scale structure is shaped by gravity acting on matter over cosmic time. These patterns emerged from tiny density differences in the early universe, amplified gradually as matter attracted more matter. To clarify, galaxies did not form randomly. Their positions reflect the underlying structure of space-time, shaped shortly after the universe began. This matters because it shows that order can arise without design, purely through physical laws. You can observe this as a quiet consistency rather than a dramatic revelation. There's no need to resolve it now. The structure remains, waiting as the narrative continues. We remain within that same wide view. Nothing closes, nothing concludes. The galaxy and its neighbors still occupy the same calm mental space. You might now imagine stepping back even further, not to see more detail, but to allow the image to soften. Each galaxy, with all its stars and history, is one part of a much larger pattern, yet it remains complete on its own terms. This balance between individuality and participation is a factual feature of cosmic structure. Galaxies are autonomous systems, but they also belong to a connected universe. There's no hierarchy implied here, only scale. For you as a listener, this can simply register as context rather than meaning. No action follows from it. The mind doesn't need to carry everything forward. It can let some details fade while others remain. And with that gentle loosening, we move onward without ending anything at all. The wide view remains with us, unchanged in its calm. We are still surrounded by galaxies, still holding the idea that they exist as stable systems within a larger structure. Nothing from before needs to be repeated or reinforced. You might picture one galaxy slowly becoming clearer, not brighter, just more defined in outline. Its light gathers into a recognizable form, neither sharp nor symmetrical in an obvious way. Galaxies come in different shapes, which astronomers classify using observable structure rather than origin or age. The three broad categories are spiral, elliptical, and irregular. These are descriptive labels based on appearance, not judgments or stages. This classification emerged in the early 20th century as telescopes improved and patterns became easier to compare across many galaxies. The importance of shape is practical. Structure reflects how stars and gas are arranged and how they move. As an observer, you don't need to remember the names precisely. Simply noticing that galaxies are not all alike is enough. The image can remain soft as we continue without closing anything. That first sense of structure carries forward naturally. We're still looking at galaxies from a distance that allows form to be seen without detail. Imagine a galaxy with long, curved arms extending from a bright center, turning slowly through space. Spiral galaxies are characterized by flat, rotating disks with spiral arms made of stars, gas, and dust. Many also contain a central bulge, a dense region of older stars near the core. Our own Milky Way is a spiral galaxy, though we observe it from within rather than from the outside. The spiral arms are not rigid structures. They are regions of higher density that move through the disk, compressing gas and triggering star formation as they pass. This matters because it explains why spiral arms often appear bright and active. You can notice this as a relationship between shape and ongoing change, rather than as a dramatic process. The idea doesn't demand attention. It can stay gently present as we move on. The spiral form fades slightly as the focus widens again. We're not leaving it behind, only making room for another shape to appear alongside it. Picture a galaxy that looks smooth and rounded, without arms or obvious internal patterns. Its light is evenly spread, like a soft glow against darkness. Elliptical galaxies have shapes ranging from nearly spherical to elongated ovals. They lack the flat disks and spiral arms seen in spiral galaxies and contain relatively little cold gas or dust. Most stars in elliptical galaxies are older, and new star formation is minimal. The stars move in more random orbits rather than following a shared rotational plane. To clarify, elliptical galaxies are not unfinished spirals. They represent a different structural state. This distinction matters because it reflects differences in motion, composition, and history. As a listener, you can simply register the contrast without needing to assign cause. The image can remain quiet and incomplete as we continue. The presence of smooth, rounded galaxies remains in the background as we allow another form to enter gently. Imagine a galaxy without a clear shape at all. Its light appears uneven, scattered, and asymmetrical, as if it never settled into a stable pattern. Irregular galaxies lack the defined structures seen in spirals and ellipticals. They often result from gravitational interactions, such as close encounters or mergers with other galaxies. These interactions can disrupt ordered motion, pulling stars and gas into uneven distributions. Irregular galaxies are often rich in gas and actively forming new stars, despite or because of their lack of symmetry. This matters because it shows that disorder does not imply inactivity. In some cases, disruption increases change rather than halting it. You can observe this simply as variety, not as a problem to solve. The thought doesn't need to resolve. It can remain open as the narrative moves forward. All three shapes now exist together in the same mental space. Nothing needs to be emphasized. The categories can sit quietly beside one another. You might imagine a slow transition between forms, not as a rule, but as a possibility. Galactic shapes can change over time, especially through mergers. When galaxies collide, their structures can be altered dramatically, often resulting in an elliptical galaxy. These collisions are slow, unfolding over hundreds of millions of years. Stars rarely collide directly, but gravitational forces reshape entire systems. To clarify, mergers are common in cosmic history and play a major role in shaping large galaxies. This matters because it connects shape to long-term interaction rather than to isolated development. As an observer, you can simply note that galaxies are not fixed in form forever. The idea can remain unfinished, allowing space for what follows. The sense of slow change continue without interruption. We remain within the same calm frame, where time stretches far beyond immediate experience. Imagine two galaxies passing close enough to feel each other's gravity, their shapes subtly bending. Even without merging, gravitational interactions can distort galaxies, creating tidal tails, warped disks, or extended streams of stars. These features are evidence of past encounters, preserved in structure long after the interaction occurred. To clarify, galaxies carry physical memory. Their shapes record events that happened millions or billions of years earlier. This is significant because it allows astronomers to reconstruct cosmic history by observing form. You don't need to follow that reconstruction. Just noticing that shape contains information is enough. The image can soften again, making room for the next idea without closing this one. We remain in that softened view. The galaxies are still present, but their outlines no longer demand attention. You might imagine stepping back just enough to see shape as one property among many, not the defining feature. Galactic classification is a tool, not a complete description. Shape tells us something real, but not everything about a galaxy's mass, age, or future. This matters because it reminds us that scientific categories simplify reality in order to make patterns visible. As a listener, you're not required to hold on to these labels. They exist to support understanding, not to test memory. The mind can release what it doesn't need and keep what feels useful. Nothing ends here. The galaxies remain, quietly changing as we continue onward. the shapes of galaxies remain loosely in view as we continue, without needing to return to them directly. Nothing has shifted in purpose. We're still observing, still letting structure give way to quieter details. You might imagine a galaxy again, not as a shape this time, but as a faint mixture of light and shadow, layered rather than outlined. At the most basic level, galaxies are composed of stars, interstellar gas, interstellar dust, and dark matter. These components differ greatly in how visible they are, but all contribute to the galaxy's behavior. Stars dominate what we see because they emit light. Gas and dust often reveal themselves indirectly by absorbing or scattering starlight. This distinction matters because visibility does not correspond to importance. Some of the most influential components are the least obvious. You don't need to separate these elements clearly in your mind. Simply knowing that galaxies are mixtures, not uniform objects, is enough. The idea can remain lightly held as we continue. That sense of mixture continues naturally. We're still within the same galaxy, just allowing attention to rest on one component at a time. Picture a field of stars spread through space, each one isolated, yet part of a collective glow. Stars are the primary luminous component of galaxies. They vary widely in mass, temperature, and lifespan, but all produce energy through nuclear fusion in their cores. In most galaxies, the majority of visible light comes from stars similar to our Sun, even though more massive stars shine more brightly for shorter periods. To clarify, stars are not evenly distributed. They cluster in disks, bulges, or halos, depending on the galaxy's structure. This matters because the distribution of stars shapes a galaxy's appearance and evolution. As an observer, you don't need to track individual stars. Their collective presence is what matters here. The image can soften again, remaining present but unforced. The stellar glow remains, but now it feels incomplete on its own. Something else occupies the space between the stars. You might imagine faint clouds, barely visible, drifting slowly in the darkness between points of light. Interstellar gas, primarily hydrogen and helium, fills much of the space between stars and galaxies. Though extremely diffuse, its total mass can be substantial. This gas exists in different states, from cold molecular clouds to hot ionized regions. The coldest and densest clouds are the sites where new stars can form. To clarify, star formation does not happen everywhere. It requires specific conditions of density and temperature within these gas clouds. This matters because gas is the raw material for future stars. You can simply note that galaxies are not finished products. They contain the means for ongoing change. The idea doesn't need to go further right now. It can remain gently open. That presence of gas leads naturally to another, subtler component, still without altering the overall calm. Imagine that same interstellar space, now with fine grains suspended within it, almost invisible. Interstellar dust consists of tiny solid particles made of elements like carbon, silicon, and oxygen. These grains are comparable in size to smoke particles and make up only a small fraction of a galaxy's mass. Despite this, dust plays an outsized role in shaping what we observe. It absorbs and scatters visible light, obscuring some regions while revealing others at different wavelengths. To clarify, dust does not float freely forever. It forms in dying stars and can later become part of new planetary systems. This matters because dust connects stellar death to future formation. As a listener, you don't need to visualize the grains precisely. their effect is more important than their appearance. The thought can remain light as we move on. With stars, gas, and dust present together, the galaxy begins to feel layered rather than empty, yet something still remains unseen. You might imagine a quiet gravitational presence, shaping motion without producing light. Dark matter makes up most of a galaxy's mass. It does not interact with light, but its gravitational influence determines how stars and gas move. Evidence for dark matter comes from observing galactic rotation and the motion of galaxies within clusters. Visible matter alone cannot account for these movements. To clarify, dark matter is not a correction or assumption. It is a consistent explanation supported by multiple independent observations. This matters because without dark matter, galaxies as stable systems would not exist in their observed forms. You don't need to imagine dark matter directly. Its presence is inferred, not seen. The idea can rest quietly, without resolution. That unseen mass remains part of the background as we continue, without becoming heavier or more abstract. You might imagine all these components moving together, responding to the same gravitational framework. The interaction between stars, gas, dust, and dark matter governs a galaxy's evolution. Changes in one component affect the others over long timescales. For example, gas distribution influences star formation, which in turn affects light output and chemical composition. To clarify, no component acts alone. Galactic behavior emerges from interaction rather than dominance. This matters because it frames galaxies as dynamic systems rather than collections of separate parts. As an observer, you can simply note that complexity here is gradual and cooperative. The thought doesn't need to be held tightly. It can remain diffuse as we continue. The galaxy remains present, now understood as a layered system, even if the details begin to blur again. You might imagine stepping back slightly, letting the distinctions soften. What a galaxy is made of tells us not only what it looks like now, but what it can become over time. Composition sets possibilities without determining outcomes. This is a factual constraint, not a narrative arc. For you, this can register as context rather than conclusion. No summary is required. Some elements may fade from immediate awareness, while others linger faintly. Nothing ends here. The galaxy continues, composed and recomposing itself, as we move gently onward. The layered composition of galaxies remains quietly in place as we continue. Nothing has been resolved or set aside. Stars, gas, dust, and unseen mass are still present, simply waiting for the next idea to rest among them. You might imagine the galaxy slowly dissolving backward in time, not disappearing, but becoming less defined, as if its structure were loosening. Galaxies did not appear fully formed. They emerged gradually from the early universe as matter responded to gravity. Small variations in density, present shortly after the universe began, provided the initial seeds. These slightly denser regions attracted more matter over time, growing slowly through gravitational accumulation. This matters because galaxy formation was not a sudden event. It was a prolonged process governed by the same physical laws that operate today. You don't need to picture the early universe clearly. Just knowing that galaxies had beginnings rooted in small differences is enough. The idea can remain open as we continue backward gently. That backward motion continues without interruption. We're still moving toward earlier conditions, not rushing, not condensing time too sharply. You might imagine a universe filled with diffuse gas, almost uniform, with no distinct objects yet visible. In the early universe, most matter existed as hot gas, primarily hydrogen and helium. As the universe expanded and cooled, gravity began to draw this gas into growing concentrations. Dark matter played a central role in this process. Because it does not interact with radiation, it began clumping earlier than ordinary matter, forming gravitational wells. To clarify, normal matter fell into these dark matter structures, not the other way around. This matters because it explains why galaxies formed where they did, following an underlying framework. As a listener, you can simply note that unseen structure preceded visible form. The idea doesn't require completion. It can remain suspended as we move on. That framework remains present as we continue, unchanged in its quiet influence. You might imagine matter slowly streaming inward, guided by gravity, collecting without urgency. As gas accumulated within dark matter halos, it began to cool and condense. Cooling allowed gas to lose energy, making it possible for it to collapse further and eventually form stars. The first stars formed within these early structures, marking the transition from a dark universe to one filled with light. To clarify, cooling is essential. Without it, gas would remain too energetic to settle into dense regions. This matters because star formation depends on physical conditions, not timing or chance. You don't need to imagine the first stars vividly. Their emergence can remain abstract and distant. The thought can rest here briefly, without moving toward conclusion. The presence of early stars remains softly in the background as we continue forward in time again. You might imagine small galaxies forming first, simple and compact, before larger ones exist. Early galaxies were smaller and less structured than many galaxies observed today. Over time, they grew through continued gas accretion and mergers with other small galaxies. This hierarchical growth is a key feature of modern cosmology. Large galaxies are built from the accumulation of smaller ones. To clarify, this does not imply constant collision. Growth occurred through a combination of merging and gradual material inflow. This matters because it connects present-day galaxies to a long history of assembly rather than singular origin. As an observer, you can simply note that size reflects history. The idea can remain incomplete as we move gently onward. That sense of gradual assembly continues, without shifting pace or tone. You might imagine galaxies drifting closer together over vast stretches of time, responding to mutual gravity. When galaxies merge, their stars largely pass by one another, but their gas clouds interact strongly. This can trigger bursts of star formation and alter the final structure. Major mergers often transform disk galaxies into elliptical ones, redistributing stars into more random orbits. To clarify, mergers are transformative events, but they unfold slowly and predictably under gravity. This matters because dramatic changes in appearance arise from calm, extended processes. You don't need to follow the details of a merger. Just recognizing its long time scale is enough. The thought can remain softly present as we continue. The image of merging systems fades slightly, leaving behind a sense of continuity rather than disruption. You might imagine galaxy formation as ongoing rather than finished. Even today, galaxies continue to form stars, accrete gas, and interact with their surroundings. While the peak era of galaxy formation lies in the distant past, the process has never fully stopped. To clarify, galaxy formation is not a closed chapter in cosmic history. It remains active, though slower. This matters because it places the present universe within the same physical story as the past. As a listener, you can simply note that galaxies are still becoming, not merely existing. The idea does not require closure. It can remain gently unresolved. All of these stages now coexist quietly: early density variations, dark matter scaffolding, gas cooling, star formation, and gradual growth. You might imagine the galaxy again as it is now, carrying traces of all those earlier conditions within its structure. Galaxy formation leaves lasting imprints. The distribution of stars, the presence of a halo, and the motion of material all reflect how a galaxy assembled. This is not a narrative conclusion, just a physical consequence. For you, this can register as background awareness rather than focused knowledge. Some details may drift out of attention, others may linger faintly. Nothing ends here. The galaxy remains, formed and still forming, as we move quietly onward. The idea of galaxies still forming carries forward naturally. Nothing has closed behind us. We remain within systems that continue to change, slowly and without urgency. You might picture a galaxy again, familiar now, but with attention drifting inward, toward darker, denser regions embedded within its light. Star formation occurs inside galaxies, not uniformly, but in specific environments. It begins within cold, dense clouds of gas known as molecular clouds, where gravity can overcome internal pressure. These clouds are mostly hydrogen, with small amounts of heavier elements and dust mixed in. Their density allows them to shield themselves from radiation, enabling further cooling. This matters because stars do not appear randomly. Their birth depends on physical conditions that are rare compared to the overall size of a galaxy. You don't need to visualize the clouds precisely. Just knowing that stars form in protected pockets is enough. The image can remain quiet as we move onward. Those dense regions remain present as the narrative continues, without pulling focus too sharply. You might imagine a molecular cloud slowly contracting, not collapsing all at once, but fragmenting gently. Within a collapsing cloud, gravity causes denser clumps to form. Each clump can become a protostar, gradually heating as material falls inward. When the core temperature becomes high enough to ignite nuclear fusion, a new star is born. This moment is defined physically, not visually. To clarify, star formation is inefficient. Only a small fraction of a cloud's mass becomes stars. The rest is dispersed back into the galaxy. This matters because galaxies regulate their own growth. Star formation does not consume all available material at once. As an observer, you can simply note that creation here is partial and measured. The idea doesn't need resolution. It can remain open. The presence of newborn stars lingers softly as we continue, without shifting attention away from the broader system. You might imagine clusters of young stars forming together, rather than in isolation. Stars often form in groups, sharing a common origin within the same cloud. These stellar nurseries can produce hundreds or thousands of stars over relatively short cosmic timescales. Massive stars, though rare, have a strong influence. They emit intense radiation and stellar winds that shape their surroundings. To clarify, these effects can both trigger and suppress further star formation nearby. This matters because star formation is self-modifying. The first stars change the conditions for the next. You don't need to track individual outcomes. Just noticing the feedback is enough. The image can soften again as we continue. That feedback remains part of the background as time advances within the galaxy. You might imagine some stars burning steadily for billions of years, while others change much more quickly. The mass of a star determines its lifespan. Massive stars burn fuel rapidly and live only millions of years, while smaller stars can persist for tens or hundreds of billions of years. This difference affects galaxies over time. Short-lived massive stars enrich the surrounding gas with heavier elements when they die. To clarify, these elements are produced through nuclear processes inside stars and released through stellar winds or explosions. This matters because future generations of stars form from enriched material, gradually changing galactic composition. As a listener, you can simply note that star formation is cumulative. The idea can remain unfinished as we move forward. The cycle of formation and enrichment continues without interruption. Nothing concludes here. You might imagine regions of a galaxy glowing more brightly, where star formation is active. In spiral galaxies, star formation often concentrates in spiral arms, where gas is compressed by density waves. In elliptical galaxies, star formation is usually minimal due to lack of cold gas. To clarify, environment strongly influences star formation rates. This matters because the appearance of a galaxy reflects how actively it is forming stars. You don't need to memorize which galaxies form stars fastest. Just noting the connection between structure and activity is enough. The image can remain gentle as we continue. That activity slowly ebbs in some regions while continuing in others, without any sense of finality. You might imagine star formation gradually slowing as gas is consumed or expelled. Galaxies can exhaust or lose their star-forming gas through stellar feedback, galactic winds, or interactions with their surroundings. When this happens, star formation declines. To clarify, this process is gradual and reversible in some cases if new gas is acquired. This matters because it explains why galaxies change appearance over time without requiring sudden events. As an observer, you can simply note that galaxies age, but not all in the same way. The thought can remain open. All of these processes remain quietly interconnected: cloud collapse, stellar birth, feedback, enrichment, and gradual change. You might imagine the galaxy again as a whole, its light shaped by countless individual stars formed across deep time. Star formation links small-scale physics to large-scale structure. The behavior of gas clouds ultimately determines how a galaxy looks and evolves. This is not a conclusion, only a continuity. For you, this can remain as background awareness rather than focused understanding. Some details may fade, others may remain faintly present. Nothing ends here. The galaxy continues, forming stars at its own unhurried pace as we move gently onward. The quiet cycle of star formation remains present as we move forward, without needing to revisit its details. The galaxy is still there, carrying both older stars and newly formed ones, all sharing the same space. You might imagine that space now in motion, not hurried, not chaotic, just gently active. Points of light trace slow paths, repeating patterns too large to notice at once. Inside a galaxy, stars are constantly moving. Their motion is governed by gravity, responding to the combined mass of everything around them. In disk galaxies, most stars follow roughly circular orbits around the galactic center. This ordered motion creates large-scale structure. The overall shape of a galaxy is not fixed in place, but sustained by continuous movement. This matters because stability does not mean stillness. Galactic order is maintained through motion rather than despite it. As an observer, you don't need to imagine each orbit precisely. Just knowing that movement is continuous and coordinated is enough. The idea can remain gently active as we continue. That sense of motion carries forward without any sharp shift. We are still inside the galaxy, still watching patterns unfold slowly. You might picture the galactic center as a region of greater brightness and density, drawing everything inward without pulling it directly in. Stars closer to the center of a galaxy orbit more quickly than those farther out. This difference arises because gravitational influence changes with distance and mass distribution. In disk galaxies, this creates differential rotation. The inner regions complete an orbit faster than the outer regions, stretching patterns over time. To clarify, galaxies do not rotate like solid objects. Their parts move independently, guided by gravity rather than rigidity. This matters because differential motion shapes features like spiral arms and bars. You can simply note that variation in speed is a natural outcome of gravity. The thought can rest here without conclusion. The varying speeds of stars remain present as we continue, without drawing attention away from the broader system. You might imagine spiral arms again, not as fixed structures, but as gently shifting regions within the disk. Spiral arms are often described as density waves. They are areas where stars and gas temporarily crowd together as they orbit the galactic center. As gas enters these regions, it compresses, often triggering star formation. As it leaves, the process quiets again. To clarify, the stars themselves move in and out of spiral arms. The arms persist as patterns rather than collections of the same stars. This matters because it explains how spiral structure can remain visible over long periods. As a listener, you don't need to hold on to the mechanics. Just noticing that pattern and motion coexist is enough. The image can soften again as we move on. That coexistence of motion and pattern continue without interruption. The galaxy remains balanced, even as everything within it moves. You might now imagine stars moving in less orderly paths, especially away from the disk. In galactic halos and elliptical galaxies, stellar motion is more random. Stars move in many directions, forming a roughly spherical distribution. This difference reflects how these systems formed and evolved. Ordered rotation dominates where disks exist. Random motion dominates where they do not. To clarify, neither type of motion is more advanced or primitive. They are outcomes of different histories. This matters because motion preserves memory. How stars move tells us how the system came to be. You don't need to decode that history. Simply knowing it exists is enough. The idea can remain lightly present. The contrast between ordered and random motion remains quietly in view as we continue. You might imagine the galaxy responding subtly to disturbances, adjusting rather than breaking. Galaxies can absorb small disruptions, such as minor mergers or internal instabilities. By redistributing motion, stars shift orbits, gas flows change, and balance is restored over time. This self-regulation arises from gravity acting across the entire system. To clarify, galaxies are not fragile. Their size and mass allow them to smooth out many disturbances. This matters because it explains their longevity across billions of years. As an observer, you can simply note that large systems change slowly and resist sudden collapse. The thought can remain open as we move on. That resilience continues to sit quietly in the background. You might imagine the galaxy interacting with its environment, not isolated, but not overwhelmed either. Galaxies are influenced by their surroundings. Nearby galaxies, intergalactic gas, and gravitational fields all affect motion at the edges. These influences can alter orbits, strip gas, or trigger new internal motion, especially in dense environments like clusters. To clarify, environment shapes motion without determining every outcome. This matters because galaxies are part of larger systems, even while remaining coherent on their own. You don't need to picture the entire environment. Just knowing it exists is enough. The idea can remain gently unresolved. All this motion ordered, random, internal, and external continues quietly at once. You might imagine stepping back again, letting the details blur into a general sense of movement. A galaxy's structure is maintained not by stillness, but by continuous, balanced motion across immense timescales. This is not a conclusion, only a physical condition. For you, this can register as background awareness rather than focused insight. Some patterns may fade, others may linger faintly. Nothing ends here. The galaxy continues moving, slowly and steadily, as we drift onward. The slow motion of stars remains with us as we continue, unchanged in its calm rhythm. Nothing has concluded. The galaxy is still moving, still balanced, still quietly held together by gravity. You might imagine drifting toward the center of a galaxy now, not rapidly, just gradually, as if attention itself were moving inward. At the centers of most large galaxies lies a supermassive black hole. These objects contain millions to billions of times the mass of the Sun, concentrated into an extremely small region. Their presence is inferred through their gravitational effects on nearby stars and gas, rather than by direct observation in most cases. This matters because these black holes are not rare anomalies. They are common structural features of galaxies. You don't need to picture the black hole itself. Just acknowledging that something massive resides at the center is enough. The idea can remain quietly present as we continue. That central presence stays with us, without becoming dominant or dramatic. You might imagine stars orbiting near the galactic core, their paths tightening as gravity strengthens. Stars close to the center of a galaxy move faster, responding to the strong gravitational pull of concentrated mass. In some galaxies, precise measurements of these motions provide clear evidence for a supermassive black hole. The orbits are stable over long periods, despite the extreme mass involved. To clarify, black holes do not pull everything inward indiscriminately. Objects orbit them much like planets orbit stars, as long as they remain at a safe distance. This matters because it corrects a common misunderstanding. The presence of a black hole does not disrupt the entire galaxy. As an observer, you can simply note that even extreme objects obey familiar physical laws. The image can remain calm as we continue. The central region remains in view, softly illuminated by surrounding stars. You might imagine gas drifting inward, gradually, not falling straight in, but spiraling gently. When gas approaches a supermassive black hole, it can form an accretion disk. Friction and compression within this disk heat the gas, causing it to emit radiation. In some galaxies, this process produces an active galactic nucleus, which can outshine the rest of the galaxy. To clarify, not all central black holes are actively accreting material. Many remain quiet for long periods. This matters because activity depends on available gas, not on the black hole's existence alone. You don't need to imagine the brightness precisely. Just knowing that energy can be released here is enough. The thought can remain open. That potential for activity lingers as we continue, without becoming the focus. You might imagine powerful energy flowing outward from the center, interacting with the surrounding galaxy. Active black holes can produce jets and winds that extend far beyond the central region. These outflows can heat or expel gas from the galaxy's inner areas. This process is known as feedback. It influences how much gas remains available for star formation. To clarify, feedback can both suppress and regulate growth rather than simply stopping it. This matters because it links the smallest scales near a black hole to the largest scales of galactic evolution. As a listener, you don't need to follow the mechanics closely, just noting the connection is enough. The image can soften again as we continue. The galaxy remains whole, even with such energetic processes occurring near its center. You might imagine long periods of quiet, interrupted occasionally by activity. Most supermassive black holes spend much of their time in a low-activity state. The dramatic phases are temporary compared to the galaxy's lifespan. To clarify, black holes grow primarily during these active periods, accumulating mass gradually over time. This matters because it places extreme phenomena within a broader, calmer context. As an observer, you can simply note that intensity here is episodic, not constant. The thought does not need closure. It can remain gently suspended. The presence of the central black hole now feels integrated rather than separate. You might imagine the galaxy again as a whole, with the center influencing structure without dominating it. There is a strong correlation between the mass of a galaxy's central black hole and properties of its stellar bulge. This suggests a linked evolutionary history. To clarify, this correlation does not imply direct control, but shared growth influenced by common conditions. This matters because it shows that galaxies evolve as interconnected systems, not as collections of independent parts. You don't need to interpret the relationship further. Just acknowledging the correlation is enough. The idea can remain open as we move on. All of this remains quietly in balance, stars in motion, gas drifting, and a massive presence at the center. You might imagine stepping back once more, allowing the central region to blend into the overall structure. The supermassive black hole is not the story of a galaxy, but it is part of the structure that shapes long-term behavior. This is not a conclusion, it's a condition that continues to unfold. For you, this can rest as background awareness rather than focused thought. Some details may fade, others may linger softly. Nothing ends here. The galaxy remains intact, centered and moving, as we continue onward. The centered galaxy remains with us as we continue, its internal motions and quiet core still present, still balanced. Nothing has resolved. We're simply widening the frame again without leaving anything behind. You might imagine the space around the galaxy becoming less empty. Faint points of light appear nearby, not as background stars, but as other galaxies, sharing the same region of space. Galaxies rarely exist in complete isolation. Most are members of larger systems known as groups or clusters, bound together by gravity. A galaxy group may contain a few dozen galaxies, while clusters can contain hundreds or even thousands. This matters because a galaxy's environment influences its long-term evolution. You don't need to imagine all members clearly. Just knowing that galaxies often have neighbors is enough. The idea can remain quietly present as we continue. That sense of company carries forward naturally, without increasing pace. You might imagine galaxies drifting slowly relative to one another, each following a long, curved path shaped by shared gravity. In galaxy groups, gravitational interactions are relatively gentle. Galaxies may pass near one another, exchanging small amounts of gas or subtly altering their shapes. These interactions occur over billions of years, unfolding gradually rather than dramatically. To clarify, close encounters do not usually involve direct collisions between stars. The vast distances between stars prevent that. This matters because it explains how galaxies can influence each other without immediate destruction. As an observer, you can simply note that proximity allows interaction without chaos. The image can remain soft as we move on. The group environment remains in view, but now it feels more structured. You might imagine a denser region where galaxies are packed more closely together, their motions more constrained. Galaxy clusters are among the most massive structures in the universe. They are held together by immense amounts of dark matter, with galaxies moving through a shared gravitational well. In clusters, galaxies can reach high velocities, sometimes thousands of kilometers per second. To clarify, this rapid motion reflects the cluster's total mass rather than any individual galaxy's behavior. This matters because it changes how galaxies evolve within clusters compared to quieter environments. You don't need to hold on to the numbers. Just noticing the difference in scale is enough. The idea can remain gently open. That dense environment now feels more active, though still unhurried in cosmic terms. You might imagine a galaxy moving through a thin, hot medium, almost like a current. Clusters contain large amounts of hot, diffuse gas between galaxies, known as the intracluster medium. As galaxies move through it, this gas can strip away their own interstellar material. This process is called ram pressure stripping. It can remove star-forming gas from a galaxy over time. To clarify, this does not tear galaxies apart. It gradually changes their internal composition. This matters because environment can reduce star formation without violent events. As a listener, you can simply note that surroundings influence internal change. The image can soften again as we continue. The galaxy, now altered slightly by its environment, continues its path within the cluster. You might imagine its gas content thinning, its light becoming dominated by older stars. Galaxies in dense environments are more likely to be elliptical or gas-poor systems. Over time, interactions and gas loss reduce their ability to form new stars. To clarify, this is a statistical trend, not a strict rule. This matters because it links large-scale structure to observable differences in galaxy populations. You don't need to classify individual galaxies. Just noticing the pattern is enough. The thought can remain unfinished. That pattern remains quietly present as we widen the view once more. You might imagine clusters themselves connected by faint bridges of matter. Galaxy groups and clusters are arranged along vast filaments of dark matter and gas, forming what is known as the cosmic web. These filaments guide the motion of galaxies over immense distances. To clarify, this structure emerged from the same early density variations that shaped individual galaxies. This matters because it shows continuity across scales, from single galaxies to the largest structures in the universe. As an observer, you can simply note that galaxies belong to a larger pattern. The image can remain spacious and unresolved. All of this remains quietly interconnected individual galaxies, groups, clusters, and filaments. You might imagine stepping back just enough to see galaxies not as isolated objects, but as participants in a shared gravitational landscape. A galaxy's story is shaped not only by its internal processes, but also by where it resides in this larger structure. This is not a conclusion, only a context. For you, this can register as background awareness rather than focused understanding. Some details may fade, others may remain faintly present. Nothing ends here. The galaxies continue together, moving through shared space. As we drift onward, the shared motion of galaxies within larger structures remains quietly in place as we continue. Nothing has closed. The cosmic web still stretches outward, holding galaxies in its subtle geometry. You might imagine that same scene now being viewed from far away, not from within space itself, but through an instrument, patient and still. Our understanding of galaxies comes from observation, carried out with telescopes that collect light across vast distances. These instruments do not reach out physically. They wait, allowing light to arrive on its own time. Every observation depends on photons that have traveled for millions or billions of years before being detected. This matters because astronomy is inherently historical. We never see galaxies as they are now, only as they were when their light began its journey. You don't need to think about the technology yet. Just noticing that observation itself has limits is enough. The idea can remain gently open as we continue. That act of waiting remains central as we move forward, without shifting pace. You might imagine a telescope as a quiet surface, gathering faint signals rather than projecting anything outward. Optical telescopes observe visible light, the same narrow range detected by human eyes. They reveal stars, dust lanes, and overall galactic structure. However, visible light is easily blocked by dust, both within galaxies and between them. To clarify, what we see in visible light is incomplete. It highlights certain components while hiding others. This matters because early images of galaxies reflected the limits of the wavelengths being observed. As an observer, you can simply note that visibility depends on how we look, not only on what exists. The image can remain calm as we continue. That limitation leads naturally to a broader view, still without urgency. You might imagine the same galaxy observed again, now revealing different features, as if another layer had become visible. Astronomers observe galaxies across the electromagnetic spectrum, including radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each wavelength reveals different physical processes. Infrared light penetrates dust and highlights cooler objects, such as star-forming regions. Radio waves trace cold gas. X-rays reveal high-energy environments. To clarify, no single image shows a complete galaxy. Each wavelength contributes a partial view. This matters because understanding galaxies requires combining many observations rather than relying on one perspective. You don't need to remember which wavelength shows what. Just noticing that multiple views exist is enough. The idea can remain lightly present. Those multiple views remain layered together as we continue, without demanding integration. You might imagine images being compared side by side, not to judge them, but to see how they differ. By studying galaxies at different wavelengths, astronomers infer properties like star formation rates, gas content, and energetic activity near galactic centers. These inferences are grounded in well-tested physical laws linking radiation to temperature, motion, and composition. To clarify, astronomers do not guess randomly. Observations are interpreted through models that can be tested and refined. This matters because scientific understanding grows through consistency across independent measurements. As a listener, you can simply note that interpretation is careful and cumulative. The thought can remain open as we move on. The act of observation now feels less passive, though still quiet. You might imagine light being spread out into a spectrum, its colors separated and measured precisely. Spectroscopy allows astronomers to analyze the light from galaxies in detail. By examining spectral lines, they determine composition, temperature, and motion. Shifts in these lines reveal how fast a galaxy is moving toward or away from us, through the Doppler effect. To clarify, this motion reflects the expansion of the universe as well as local dynamics. This matters because motion provides distance estimates and places galaxies within cosmic history. You don't need to follow the mathematics. Just knowing that light carries detailed information is enough. The image can soften again. That detailed information remains quietly embedded in the light as we continue. You might imagine observing many galaxies at different distances, each one appearing at a different stage of development. Because light takes time to travel, surveys of distant galaxies effectively sample different eras of the universe. This allows astronomers to study how galaxies change over cosmic time, even though no single galaxy can be watched evolve directly. To clarify, this is not reconstruction from imagination. It is comparison across distance and time. This matters because it connects observation to understanding of evolution. As an observer, you can simply note that distance becomes a tool, not an obstacle. The idea can remain unresolved. All of these methods, imaging, spectroscopy, and multi-wavelength observation, remain quietly in use at once. You might imagine the galaxy again, unchanged in itself, but gradually becoming clearer through accumulated observation. Our picture of galaxies is not built from a single discovery, but from many small, careful measurements layered over time. This is not a conclusion, only a process. For you, this can rest as background awareness rather than focused knowledge. Some details may drift away, others may linger faintly. Nothing ends here. Observation continues patiently as we move onward. The patient act of observation remains with us as we continue, unchanged in character. Nothing has concluded. Light still arrives slowly, carrying information from different distances and different moments. You might imagine that same galaxy now placed along a long timeline, not marked with dates, but with depth. Nearer galaxies feel close in time. Distant ones feel faint and ancient. Because light travels at a finite speed, observing galaxies at different distances means observing different epochs of the universe. A nearby galaxy is seen as it was relatively recently. A very distant galaxy is seen as it was when the universe was much younger. This matters because space and time are linked in astronomy. Distance becomes a proxy for age. You don't need to calculate how far or how old. Simply noticing that looking farther means looking earlier is enough. The idea can remain gently open as we continue. That link between distance and time stays quietly present as we move forward. You might imagine galaxies arranged not across space, but along a slow gradient of age, fading subtly as they recede. In the early universe, galaxies were generally smaller, more compact, and more actively forming stars than many galaxies today. Observations of distant galaxies consistently show higher rates of star formation. This reflects conditions at the time. Gas was more abundant, and interactions between galaxies were more frequent. To clarify, this does not mean early galaxies were chaotic. They followed the same physical laws, but under different conditions. This matters because it shows that galaxies change systematically over cosmic time. As an observer, you can simply note that activity levels are not constant across history. The thought can remain unfinished. That early activity lingers in the background as we continue along the timeline. You might imagine galaxies gradually settling, their intense brightness softening as time passes. As the universe aged, star formation rates declined. Gas was either converted into stars, heated, or expelled from galaxies, reducing the material available for new star birth. This decline is observed across many environments and galaxy types. To clarify, this is a global trend, not a uniform rule for every individual galaxy. This matters because it places the present-day universe within a long-term transition rather than a steady state. You don't need to focus on the decline itself. Just noticing change over time is enough. The image can remain calm as we move on. The sense of gradual change continue without interruption. You might imagine galaxies becoming more structured over time, their form stabilizing. Over billions of years, repeated interactions and internal evolution shaped galaxies into the diverse population observed today. Disk galaxies became more defined. Elliptical galaxies grew larger through mergers. To clarify, this process did not move toward a single outcome. Diversity increased rather than converged. This matters because it shows that cosmic evolution produces variety, not uniformity. As a listener, you can simply register that present-day galaxies are the result of long, branching histories. The idea can remain softly present. That diversity now feels grounded in time rather than in classification alone. You might imagine observing the same type of galaxy at different distances, noticing subtle differences. Galaxies of similar mass and shape can look different depending on when they are observed in cosmic history. Younger versions tend to be more gas-rich and actively forming stars. To clarify, classification does not fix a galaxy's properties across time. This matters because it prevents us from treating galaxy types as static categories. You don't need to track specific examples. Just noticing that time modifies similarity is enough. The thought can remain unresolved. The timeline stretches quietly in both directions now. You might imagine the future of galaxies as an extension of the same slow processes. As star formation continues to decline, many galaxies will become dominated by long-lived, low-mass stars. Their light will grow dimmer and redder over time. To clarify, this is not a prediction of disappearance, but of gradual change. This matters because galaxies are not temporary features. They evolve slowly even on the longest scales. As an observer, you can simply note that the future follows from the same physics as the past. The idea can remain open. All of this past, present, and future coexists quietly in the concept of a galaxy. You might imagine the galaxy again, unchanged in appearance, but now carrying time within it. Every galaxy observed today contains stars formed at different epochs, preserving a record of cosmic history in its composition and motion. This is not a conclusion, it's a continuity. For you, this can rest as background awareness rather than focused understanding. Some details may fade, others may linger softly. Nothing ends here. Time continues to pass through galaxies, slowly and without urgency. As we move onward, the long sense of cosmic time remains gently present as we continue. Nothing has been resolved or set aside. Galaxies still carry their histories, moving forward through the same physical laws that shape their past. You might imagine the space between galaxies now, not empty, but quietly stretching, almost imperceptibly, as if distance itself were changing. The universe is expanding. This expansion means that, on large scales, galaxies are moving away from one another as space itself grows. The motion is not caused by galaxies traveling through space, but by space expanding between them. This matters because the large-scale arrangement of galaxies is shaped not only by gravity, but by cosmic expansion. You don't need to picture the expansion dynamically. Just knowing that distances increase over time is enough. The idea can remain softly open as we continue. That expansion remains present without becoming urgent or dramatic. You might imagine distant galaxies slowly drifting farther apart, their light thinning as it travels across increasing space. As the universe expands, light traveling through it is stretched to longer wavelengths, a phenomenon known as redshift. The more distant a galaxy is, the more its light is shifted. This relationship allows astronomers to estimate how far away galaxies are and how quickly the universe is expanding. To clarify, redshift is not caused by galaxies burning cooler or dimmer. It is a property of expanding space. This matters because it links observation directly to the large-scale behavior of the universe. As an observer, you can simply note that light carries information about expansion. The image can remain calm as we move on. That stretched light lingers gently as we continue, without pulling focus. You might imagine measuring the distances to many galaxies, each one contributing a point to a larger pattern. In the early 20th century, observations revealed that more distant galaxies show greater redshift. This relationship demonstrated that the universe is expanding uniformly in all directions. This expansion does not have a center. Every galaxy observes others moving away, regardless of location. To clarify, expansion is not an explosion from a single point. It is a property of space itself. This matters because it reframes how we think about motion on cosmic scales. You don't need to resolve the geometry. Just noticing that expansion has no center is enough. The thought can remain unfinished. The idea of expansion now feels integrated rather than separate. You might imagine gravity and expansion existing together, not in conflict, but in balance. On small scales, such as within galaxies or clusters, gravity dominates. Galaxies remain bound, their internal motions unaffected by cosmic expansion. On larger scales, expansion becomes the dominant influence, shaping how clusters and filaments separate over time. To clarify, expansion does not pull galaxies apart internally. It acts where gravity is weak. This matters because it explains why galaxies remain intact even as the universe grows larger. As a listener, you can simply note that different forces operate at different scales. The idea can rest quietly. That balance between gravity and expansion continues without disruption. You might imagine very distant galaxies fading gradually, not disappearing, but becoming harder to reach with light. As expansion continues, some galaxies will eventually move beyond the observable universe. Their light will never reach us, no matter how long we wait. To clarify, this does not mean those galaxies cease to exist. They simply become unobservable from our position. This matters because observation is limited not only by technology, but by cosmic structure. You don't need to dwell on the loss. Just noticing that visibility has boundaries is enough. The image can remain soft. That sense of boundary remains quietly present as we continue. You might imagine galaxies we see today as a selected sample, shaped by both physics and perspective. The observable universe contains only the galaxies whose light has had time to reach us since the universe began. Beyond that lies more universe, structured similarly, but unseen. To clarify, what we observe is not the whole, but a horizon-defined portion. This matters because it places all astronomical knowledge within a defined context. As an observer, you can simply note that completeness is not required for understanding. The thought can remain open. Expansion, gravity, and observation now coexist quietly in the same frame. You might imagine galaxies continuing their slow evolution, while space itself continues to stretch around them. The expanding universe does not interrupt galactic life. It forms the backdrop against which galaxies persist, interact, and change. This is not a conclusion, only a condition. For you, this can rest as background awareness rather than focused insight. Some details may fade, others may remain faintly present. Nothing ends here. Space continues to expand, gently and steadily, as we move onward. The expanding universe remains quietly present as we continue, unchanged in its steady pace. Galaxies still move, space still stretches, and nothing has reached a stopping point. We are simply shifting perspective again, without introducing tension. You might imagine a familiar galaxy, still glowing softly, but now seen without labels or expectations attached to it. Galaxies are often misunderstood as dense, crowded places filled with constant activity and frequent collisions. In reality, they are mostly empty space. Even in regions with many stars, the distances between them are immense. This matters because intuition, shaped by everyday scales, doesn't translate well to cosmic ones. You don't need to correct your intuition actively. Just noticing that galaxies are far emptier than they appear is enough. The idea can remain light, clearing space for what follows. That spaciousness remains with us as we continue, without becoming abstract. You might imagine traveling through a galaxy for millions of years without encountering anything solid at all. Stars and galaxies almost never collide. The probability is extraordinarily low, even over billions of years, because the volume of space is so vast compared to the size of stars. To clarify, when galaxies merge, it is their gravitational fields and gas clouds that interact, not their stars striking one another. This matters because it reframes how we think about galactic interaction. Large changes do not require frequent impacts. As an observer, you can simply note that scale changes the meaning of interaction. The image can remain calm and open. That reframing continues gently as we move on. You might imagine a galaxy not as a single object acting with intent, but as a collection governed by simple laws. Galaxies are not purposeful systems. They do not grow, move, or change in order to achieve an outcome. Their behavior follows physical laws without direction or intention. To clarify, patterns in structure emerge naturally from gravity, motion, and energy exchange. This matters because it separates explanation from narrative. Meaning is something we apply, not something galaxies possess. You don't need to strip away wonder to accept this. Order without intentions is still order. The thought can rest here, unresolved. That absence of intention remains quietly present as we continue. You might imagine galaxies being described metaphorically, then letting those metaphors soften. Galaxies are sometimes described as alive or aging, but these are figurative terms. Scientifically, galaxies do not live, adapt, or die in the biological sense. They change state, composition, and activity level, but without metabolism or reproduction. To clarify, metaphor can aid understanding, but it should not replace physical description. This matters because clarity prevents confusion between poetic language and scientific fact. As a listener, you can simply notice when language shifts between the two. The image can remain gentle as we move on. That clarity now opens space for another quiet distinction. You might imagine a galaxy again, unchanged, simply existing without commentary. Galaxies are not isolated from uncertainty, but neither are they unknowable. While many details remain under study, much of galactic behavior is well described by established physics. Gravity, thermodynamics, and electromagnetism explain most observed features. To clarify, uncertainty in science does not imply ignorance. It reflects the boundary between what is measured and what remains to be explored. This matters because it frames scientific knowledge as provisional but reliable. You don't need to weigh confidence levels. Just knowing that understanding is partial yet grounded is enough. The idea can remain open. That grounded uncertainty remains quietly in place as we continue. You might imagine future observations refining what we already know, rather than overturning it completely. New telescopes and surveys will reveal details previously hidden, but they are unlikely to change the fundamental picture of how galaxies behave. To clarify, scientific progress is often incremental, not revolutionary. This matters because it places galaxies within a stable framework of understanding. As an observer, you can simply note that knowledge grows by addition, not erasure. The thought can remain softly present. All of this leaves the galaxy much as it was before: quiet, vast, structured, and unburdened by expectation. You might imagine releasing assumptions rather than adding conclusions. Knowing what galaxies are not helps clear space for observing what they are, without projection or urgency. This is not an ending, only a refinement of perspective. For you, this can rest as background awareness rather than focused insight. Some impressions may fade, others may remain lightly. Nothing ends here. The galaxy continues, unchanged by our interpretations, as we drift onward. The cleared perspective remains with us as we continue. Nothing has been closed or finalized. Galaxies still exist without intention, shaped quietly by physical law rather than meaning. You might imagine returning to a familiar galaxy once more, not to examine it closely, but to notice how little it resists understanding. Galaxies obey the same fundamental laws of physics as everything else in the universe. Gravity governs motion, thermodynamics governs energy flow, nuclear physics governs the behavior of stars. There are no special rules reserved for galaxies. Their immense scale does not exempt them from basic principles. This matters because it anchors cosmic phenomena in ordinary physics, extended over vast distances and times. You don't need to hold all the laws in mind. Just knowing that galaxies are lawful systems is enough. The idea can remain steady as we continue. That steadiness carries forward naturally, without increasing complexity. You might imagine equations quietly underlying the galaxy's behavior, unseen but consistent. The motion of stars and galaxies can be described mathematically. Orbital speeds, mass distributions, and stability conditions follow predictable relationships derived from gravitational theory. These descriptions do not capture every detail, but they accurately describe large-scale behavior. To clarify, predictability here does not imply simplicity. It means consistency across systems. This matters because it allows astronomers to compare galaxies separated by billions of light years using the same physical framework. As an observer, you can simply note that distance does not break the rules. The image can remain calm and unforced. That mathematical consistency remains present as we continue, without becoming abstract. You might imagine similar galaxies behaving in similar ways, even if they are far apart. Galaxies of comparable mass and composition tend to show similar structural and dynamical properties. This regularity allows astronomers to group galaxies and identify trends. To clarify, variation still exists. Regularity does not erase individuality. This matters because patterns enable understanding without requiring complete detail. You don't need to catalog the patterns. Just noticing that similarity emerges naturally is enough. The thought can remain lightly present. The presence of pattern now feels reassuring rather than restrictive. You might imagine galaxies responding predictably to familiar influences. When gas is added to a galaxy, star formation tends to increase. When gas is removed or heated, star formation declines. These responses follow well-understood physical processes. To clarify, galaxies do not choose these outcomes. They arise from energy balance and gravitational behavior. This matters because cause and effect remain intact even at cosmic scales. As a listener, you can simply note that galaxies respond rather than react. The image can soften again. That cause and effect framework remains quietly intact as we continue. You might imagine astronomers testing their understanding by comparing observation and prediction. When models based on known physics successfully reproduce observed galactic behavior, confidence grows in the underlying principles. Discrepancies lead to refinement, not abandonment of the framework. To clarify, dark matter itself emerged from such discrepancies, inferred because known laws work too well to be discarded. This matters because it shows how stability in science allows discovery. You don't need to follow the logic chain fully. Just knowing that consistency enables progress is enough. The idea can remain open. The steady application of law now feels like a quiet backdrop. You might imagine galaxies continuing their evolution without surprise, even as details vary. The future behavior of galaxies is constrained by the same physics that shaped their past. While exact outcomes are unpredictable, broad trends remain reliable. To clarify, uncertainty exists within boundaries. This matters because it places cosmic change within a framework of expectation rather than chaos. As an observer, you can simply note that large systems tend to evolve smoothly. The thought can remain gently unresolved. All of this leaves the galaxy feeling neither mysterious nor mundane, but quietly coherent. You might imagine stepping back once more, allowing the details to blur while the sense of order remains. Galaxies persist not because they resist physics, but because they follow it completely. This is not a conclusion, only a condition that continues. For you, this can rest as background awareness rather than focused understanding. Some impressions may fade, others may linger softly. Nothing ends here. The laws remain, and galaxies continue within them. As we drift onward, The steady presence of physical law remains with us as we continue. Nothing has tightened or resolved. Galaxies still follow their paths, shaped by consistency rather than exception. You might imagine a galaxy now without emphasis, without framing it as special or rare. It simply exists, one among many. Galaxies are common. Hundreds of billions are estimated to exist within the observable universe. They are not unusual structures set apart from the universe, but one of its standard outcomes. Wherever matter and gravity have had sufficient time to interact, galaxies tend to form. This matters because it shifts perspective. Galaxies are not cosmic landmarks in an empty universe. They are the texture of the universe itself. You don't need to imagine all of them. Just noticing that galaxies are widespread is enough. The idea can remain open as we continue. That sense of abundance carries forward quietly, without pressure. You might imagine space not as emptiness punctuated by rare objects, but as richly structured, even if sparsely populated at any given point. Galaxies appear wherever conditions allow matter to cool, collapse, and organize under gravity. Their presence reflects opportunity, not rarity. This is why galaxies are found in filaments, groups, and clusters rather than scattered randomly. To clarify, emptiness and abundance coexist. Most of space is empty, yet galaxies are numerous. This matters because it reframes scale. Vastness does not imply scarcity. As a listener, you can simply note that both can be true at once. The image can remain gently present. The ordinary nature of galaxies continues to unfold as we move forward. You might imagine comparing galaxies without hierarchy, without assigning importance. No single galaxy is privileged by the universe. Large galaxies are not more successful than small ones. Active galaxies are not more meaningful than quiet ones. Each reflects local conditions and long-term history. To clarify, size, brightness, and activity are descriptive properties, not measures of significance. This matters because it removes competition from cosmic structure. You don't need to rank or evaluate. Simply noticing difference without hierarchy is enough. The thought can rest quietly. That absence of hierarchy remains softly in place. You might imagine the Milky Way again, familiar, but no longer centered. Our galaxy is typical in many respects. It is neither the largest nor the smallest, neither the oldest nor the youngest, neither the most active nor the most dormant. It represents one common outcome among many possible ones. To clarify, this does not diminish its complexity or interest. It places it within a broader context. This matters because it aligns human perspective with cosmic scale. As an observer, you can simply note that familiarity does not equal centrality. The image can soften again. The sense of ordinariness now feels stabilizing rather than diminishing. You might imagine galaxies as recurring patterns rather than singular events. Given the same laws and similar conditions, galaxies tend to form again and again. Their details vary, but their existence does not require special circumstances. This repeatability is a strength of physical explanation. To clarify, predictability does not remove wonder, it grounds it. This matters because it allows understanding without reducing richness. You don't need to reconcile emotion and explanation. They can coexist quietly. The idea can remain open. That coexistence continues without interruption. You might imagine galaxies forming in distant regions of the universe, entirely disconnected from us. yet familiar in structure. Even galaxies beyond our observable horizon are expected to follow the same physical rules, forming stars, structures, and histories like those we observe. To clarify, this expectation is based on tested consistency, not assumption. This matters because it extends understanding beyond direct observation. As a listener, you can simply note that knowledge does not end at visibility. The thought can remain gently unresolved. All of this leaves galaxies feeling less distant, not in space, but in concept. You might imagine releasing the need for exception, letting galaxies be what they are. Galaxies do not require special framing to be meaningful. Their ordinariness is itself a fact of the universe. This is not a conclusion, it is a settling of perspective. For you, this can rest as background awareness rather than focused insight. Some impressions may fade, others may linger quietly. Nothing ends here. Galaxies remain, numerous and unremarkable in the best possible way. As we drift onward, the sense of ordinariness remains quietly in place as we continue. Nothing has concluded. Galaxies still exist in great numbers, following familiar laws, without requiring special emphasis. You might imagine a galaxy now partially understood, its broad features clear, its finer details still indistinct, like a landscape seen through light haze. Despite centuries of observation, galaxies are not fully understood in every detail. Certain processes, such as the precise behavior of dark matter or the fine regulation of star formation, remain areas of active research. This does not represent failure or absence of knowledge. It reflects the scale and complexity of the systems involved. This matters because scientific understanding is layered. Some aspects become clear early, while others remain unresolved for longer. As an observer, you can simply note that clarity and uncertainty coexist naturally. The idea can remain open, without discomfort, as we continue. That coexistence of knowledge and uncertainty carries forward gently. You might imagine astronomers returning repeatedly to the same galaxies, noticing new details each time. Many unanswered questions about galaxies are quantitative rather than conceptual. The broad framework is known, but exact proportions, timings, and mechanisms continue to be refined. For example, astronomers understand that feedback regulates star formation, but the precise balance varies between galaxies and environments. To clarify, these uncertainties do not undermine the framework. They exist within it. This matters because it shows how scientific confidence and curiosity operate together. You don't need to track which questions remain open. Just knowing that refinement is ongoing is enough. The image can remain calm and incomplete. That sense of ongoing refinement remains present as we continue. You might imagine future observations extending existing knowledge rather than replacing it. New telescopes allow astronomers to see fainter galaxies, earlier epochs, and finer structures. Each advance fills in gaps rather than overturning established understanding. Galaxies observed today with better instruments usually behave as expected, but with more detail. To clarify, surprise in science often comes from precision, not contradiction. This matters because it places discovery within continuity rather than disruption. As a listener, you can simply note that learning proceeds by deepening, not resetting. The thought can rest quietly. That quiet continuity remains with us as the focus broadens again. You might imagine galaxies existing independently of how well they are understood. Galaxies do not change their behavior based on observation or explanation. They continue forming stars, moving, interacting, and aging regardless of human knowledge. This separation between existence and understanding is fundamental. To clarify, ignorance does not weaken reality, and understanding does not complete it. This matters because it allows observation without urgency. You don't need to resolve every question for the subject to remain valid. The idea can remain gently suspended. The absence of urgency now feels stabilizing rather than incomplete. You might imagine knowledge as something that can remain partial without pressure to close. In astronomy, long time scales allow patience. Questions can remain open for decades without compromising progress. Galaxies themselves evolve slowly enough that understanding them does not require immediate resolution. To clarify, science does not demand total comprehension before proceeding. This matters because it allows space for curiosity without tension. As an observer, you can simply note that not knowing everything is structurally acceptable. The image can soften again. That acceptance of partial understanding continues without disruption. You might imagine galaxies as subjects that reward repeated attention rather than quick answers. Each observation adds context, not finality. Each model adds structure, not closure. This layered approach reflects the nature of the systems themselves. To clarify, galaxies are not puzzles designed to be solved, but phenomena to be described. This matters because it shapes how knowledge is framed. You don't need to adopt that framing actively. Simply noticing it is enough. The thought can remain unresolved. All of this leaves the galaxy much as it began: vast, lawful, ordinary, and partially understood. You might imagine allowing the remaining uncertainties to fade into the background. Incomplete understanding does not diminish the reality of galaxies. It simply leaves space for continued observation. This is not a conclusion. It is an ongoing condition. For you, this can rest as background awareness rather than focused insight. Some ideas may drift away, others may linger faintly. Nothing ends here. The galaxies continue, understood enough to be known, and unknown enough to remain quietly open. As this quiet exploration loosens its hold, there's nothing here that needs to stay fixed in memory. Some ideas may remain alert and clear, others may soften or drift without loss. Galaxies do not require full attention to exist, and understanding does not need completion to be meaningful. You're free to remain awake with these thoughts, or to let them recede into the background of awareness. Nothing here asks to be carried forward. The universe continues its slow work regardless. These facts can remain unfinished, uncollected, and still entirely true.